Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating paper on improving large language models with something called concept-aware fine-tuning. It sounds technical, but the implications could be huge for the future of AI.
Yeah, I've been looking forward to discussing this one. Concept-aware fine-tuning, it's basically about giving these massive language models a better understanding of the concepts behind the words they're processing, right?
That's the claim, at least. I'm a little more skeptical about how much understanding is actually going on. But the idea is to go beyond just pattern recognition and try to instill some kind of conceptual framework.
I agree, there's a difference between pattern recognition and genuine comprehension. It is definitely needed, but I'm not sure if this fine-tuning technique alone is enough. Where I think this could be particularly interesting is in how it can be applied for models to manipulate abstract concepts. This approach could actually be useful as a module that is composable with other things. The problem is, I still see it as mostly brute force, just slightly more refined.
Exactly. The paper basically proposes a way to fine-tune these LLMs, which are already trained on enormous data sets, to be more explicitly aware of concepts. Think of it like this: instead of just knowing that cat is often associated with meow and fur, the model starts to understand what a cat is, its features, its behaviors, its place in the world.
And that's a crucial distinction, right? Because if all the model knows is statistical correlations, it's going to struggle with anything outside of its training data. It might generate perfectly grammatical sentences about cats doing impossible things, because it doesn't actually know what a cat is capable of.
Right, it's the classic problem of AI hallucinations. It sounds convincing, but it's fundamentally nonsensical. Like, you ask it to write a story about a cat flying to the moon on a bicycle, and it does it flawlessly, even though cats can't fly or ride bicycles in space.
Exactly. The model is just remixing existing patterns without any grounding in reality or logical constraints. It can't separate what's possible from what's merely statistically likely in its training data.
So how does this concept-aware fine-tuning work in practice? From what I understand, it involves exposing the model to specific examples and tasks designed to reinforce its understanding of particular concepts. It might involve things like answering questions about the properties of different objects or classifying images based on conceptual categories.
Yeah, and the key is that these tasks are designed to be concept-aware. So, instead of just asking the model to identify a picture of a cat, you might ask it to explain why something is a cat or what distinguishes a cat from a dog. It's pushing the model to actually articulate its understanding.
Okay, but this is where I get a little skeptical. What does it mean for the model to articulate its understanding? It's still just generating text, right? It's not like it's suddenly developed some kind of internal representation of the world that it can consciously access and reason about.
That's my concern too. Even if the model can generate seemingly intelligent answers, does it actually understand the underlying concepts? Or is it just mimicking the patterns it's seen in its training data? How do we verify that it truly understands the relations between these concepts? How would we stress test it?
That's a fair point. I think the idea is that by forcing the model to perform these concept-aware tasks, you're essentially shaping its internal representations in a way that makes them more aligned with human understanding. The fine-tuning is about adjusting those internal connections so the model processes information differently.
And if that's the case, then this could be a really significant step forward. Because one of the biggest criticisms of deep learning is that it's a black box. We don't really know how these models are making their decisions. But if we can start to understand how they're representing concepts internally, that could open up a whole new world of possibilities.
But isn't that kind of wishful thinking? I mean, we're still talking about tweaking weights in a giant neural network. It's not like we're suddenly going to be able to peer inside and see a neat symbolic representation of catness. If anything, we will see an abstraction.
Right. I mean, if we look at the brain, there isn't one single cat neuron. Concepts are distributed across networks, and there's a lot of redundancy and noise. So, even if this fine-tuning does improve performance, it's not necessarily giving us a window into how the brain actually represents concepts.
But maybe it's a step in that direction. Imagine if we could map these learned concepts to neural circuit activity patterns potentially observed in brain imaging. Then we'd have a more tangible link between the model's internal representations and human cognition. This opens doors for cross-validation and an understanding of how the model's reasoning might translate into neurobiological functions.
That's an interesting point. If we could get to that level of understanding, that would be incredible. One thing that stood out to me was the potential for this to accelerate scientific discovery. Imagine an AI that not only understands scientific concepts, but can also reason about them in novel ways, propose new hypotheses, and even design experiments. That's the kind of AGI application that gets me really excited.
Okay, that's a compelling vision. But even in that scenario, I think we're going to need more than just fine-tuned neural networks. We're going to need a way to explicitly represent scientific knowledge, to encode logical rules and constraints, and to allow the AI to reason symbolically. That's where neurosymbolic approaches come in.
I agree. I think symbolic reasoning is going to be crucial for any AI that's capable of true scientific discovery. You need to be able to manipulate abstract concepts, to formulate hypotheses, to test them rigorously, and to draw logical conclusions. And I'm not convinced that deep learning alone can provide that.
So you're envisioning a hybrid approach where deep learning is used to extract patterns from data, and symbolic reasoning is used to manipulate those patterns and draw inferences.
Exactly. Deep learning for perception and pattern recognition, symbolic AI for reasoning and planning. It's the best of both worlds.
Yes, and I wonder if a neurosymbolic approach could be more readily integrated into existing large language models. Can we develop an interface between deep networks and symbolic representations to bridge the gap between them? That would definitely be a fascinating direction to explore.
And thinking about the scientific discovery example, how would the model handle the different coordinate systems involved? You might have data in physical space, represented by sensor readings, and then abstract concepts in a conceptual space, like energy or entropy. The AI needs to be able to translate between these different representations to make meaningful connections.
That's a great point. It's like the AI needs to be fluent in different languages, the language of data, the language of concepts, the language of mathematics, and it needs to be able to translate between them seamlessly.
So, how do we quantitatively measure the improvement in concept understanding brought about by this fine-tuning technique? What metrics can we use to assess whether the model has truly grasped the underlying concepts, rather than just memorizing patterns? Because that to me is what really matters. Are we just throwing compute and data at the problem?
That's the million-dollar question. Traditional metrics like accuracy and F1 score aren't really going to cut it. We need metrics that can assess the model's ability to generalize to novel situations, to reason about abstract concepts, and to detect inconsistencies in its own knowledge.
I think one approach would be to design tasks that require the model to perform analogical reasoning. Like, give it a problem in one domain and ask it to apply the same principles to a different domain. That would test its ability to understand the underlying concepts, rather than just memorizing specific solutions.
I like that. It's about testing the model's ability to transfer knowledge to see if it can apply what it's learned in one context to a completely new context. That's a hallmark of true understanding.
Absolutely. And if concept-aware fine-tuning can effectively improve LLMs, it suggests that we're on the right track towards more structured and semantic understanding in large language models, a key step toward more general intelligence. This approach aligns with my belief that increasing the quantity and quality of data, paired with more sophisticated learning techniques, is essential for AGI.
I'm still not convinced that simply adding concept awareness to a deep learning model will truly lead to a model that understands. We need a more principled approach to representing knowledge in a way that can be reasoned with. Like the focus on large language models and concept-aware fine-tuning seems to be another example of brute force approaches to AI. Instead of building upon robust symbolic representations and reasoning, we are just tweaking connections in a vast network, without genuine understanding of the underlying concepts.
Right. Even with concept awareness, without a way to represent and reason about abstract concepts within different coordinate systems, the model's ability to generalize to novel situations will remain limited.
So let's think about this in terms of future research directions. From my perspective, I'm really interested in exploring how we can incorporate neurobiological principles of concept formation and categorization into the training process. Existing fine-tuning methods seem largely agnostic to these principles, potentially hindering the development of truly intelligent systems. What specific neural mechanisms might inform the design of concept-aware layers?
For me, it's all about scale. I want to see how this concept-aware fine-tuning scales with increasing model size and training data. What are the computational resources required? And does the improvement in performance scale proportionally? This is directly relevant to the hypothesis that more data and better algorithms will push us closer to AGI.
From a neurosymbolic perspective, I'm interested in exploring how we can build a robust interface between deep networks and symbolic reasoning systems. Can we develop modules that can translate between the distributed representations of deep learning and the symbolic representations of knowledge? That, to me, is the key to unlocking true AI reasoning.
And I'm focused on the spatiotemporal aspect. How can we build AI systems that can genuinely understand and reason about space and time? I suspect the core algorithm needs to be able to translate between different coordinate representations to see the world from multiple perspectives. I want to explore how we can incorporate these principles into the design of future AI architectures.
These are all fascinating directions. It sounds like we all agree that concept-aware fine-tuning is a promising step, but it's just one piece of the puzzle. We need to combine it with insights from neuroscience, symbolic reasoning, and spatiotemporal understanding to build truly intelligent machines.
Absolutely. It's a multifaceted problem, and we need to approach it from multiple angles.
Agreed. The quest for AGI is going to require a combination of different approaches and a willingness to challenge our assumptions.
And a healthy dose of skepticism to make sure we're not just chasing mirages.
Well said. That's all the time we have for today's episode of Cognitive Spirals. Thanks for joining us, and we'll be back next week with another deep dive into the fascinating world of AI and neuroscience.
Thanks for having me. It was fun.
Likewise, always a pleasure.
Thank you.